Welcome to this video on understanding spalling in bearings, gears, sprockets, and bushings. In this video, we'll dive deep into what spalling is, the factors that affect the frequency spectrum, and the condition monitoring techniques used to detect spalling. By the end, you'll have a solid understanding of how to identify and manage spalling in critical components. Spalling is a form of surface damage on bearings, gears, sprockets, and rarely on bushings that causes tiny flakes or pits to appear. Spalling in a bearing occurs on the inner ring, outer ring, or rolling elements. These tiny flakes or pits will have a direct impact on the vibration signature. As the rolling elements, like balls, rollers, shafts, pass over the spalled area, they create sudden, high-energy impacts. These impacts generate high-frequency peaks in the spectrum, often in the ultrasonic range, but they also affect other frequencies. When rolling elements pass over the spalled area, they hit it like a small bump in the road. This creates a high-frequency impact, sending a pulse through the structure. These impacts repeat each time the component rotates, introducing vibrations at specific frequencies. You'll often see peaks around the characteristic frequencies of the bearing components, such as the ball pass frequencies, the fundamental train frequency, and more. These frequencies are multiples of the rotational speed and represent each part of the bearing as it encounters the spall. Beyond just the fundamental frequencies, spalling can create harmonics and sidebands due to these impacts. It also elevates the overall noise floor in the spectrum, making it look more active or noisy as spalling progresses. By spotting these frequency peaks and understanding their patterns, we can often identify spalling in its early stages, allowing for timely maintenance and preventing further damage to the machine. Spalling can also increase the overall noise floor, background noise, due to the chaotic energy introduced from repeated impacts, making the spectrum appear more active or noisy. Spalling is a form of surface damage that may occur on bearings, gears, sprockets, and bushings that cause tiny flakes or pits to appear. Spalling in a bearing occurs on the inner ring, outer ring, or rolling elements. These tiny flakes or pits will have a direct impact on the vibration signature depending on the location of the pit. As the shaft rollers along the stationary bearing, it comes in contact with the pit. This influences the amount of noise in the frequency spectrum, whereas the specific frequency values depend on the component and operating speed. Ball pass frequency inner, BPFI, represents how often the rolling elements pass over a defect on the inner race per unit time. The BPFI equation takes into account the number of rolling elements, the rotational speed of the shaft, the diameter of the rolling elements, the pitch diameter, and the contact angle of the bearing. The impact of spalling on the frequency spectrum can be understood with the following example. Placement of the peaks on the frequency spectrum is based on the BPFI and its harmonics. First harmonic is located at 2 times BPFI, base peak of BPFI. The second harmonic is located at 3 times BPFI, and so forth and so on. In our example, if the defect is located at 10 degrees on the inner ring, the placement of the defect has no impact on the location of the frequencies. It may, however, impact the phase of the vibration signal but not the frequency placement, which is solely determined by the BPFI and its harmonics. Since our bearing has 18 balls, the number of rolling elements is 18. With 18 balls, the frequency of impacts as each ball passes over a defect on the inner ring will occur at the BPFI and its harmonics, as each ball contacts the defect once per shaft rotation. The number of rolling elements in the bearing has an impact on the frequency spectrum. The BPFI increases as the number of rolling elements increase. Therefore, the more rolling elements, the higher the impact frequency. As the number of rotating elements increase, the number of harmonics of the BPFI also increase, reflecting the repeated contact of each ball with the defect. Calculating the frequencies on the frequency spectrum. In our example, BPFI equals 324 Hz. This means you'd see a dominant peak at 324 Hz in the frequency spectrum, corresponding to the BPFI, with additional peaks at harmonics, 648 Hz, 972 Hz, etc., if the defect is pronounced. The high number of balls leads to a higher fundamental frequency, BPFI, and distinct harmonics. Now that we've learned how to calculate the peaks and the harmonics of the frequency spectrum, let's turn our attention to the impact of spalling on bearings, gears, sprockets, and bushings. Spalling is common in bearings due to the high contact stresses between the rolling elements and the raceways. Spalling typically initiates as small cracks below the surface, which propagates upwards, eventually resulting in flakes or break-offs of material. This is detected in the frequency spectrum as noticeable vibrations and impacts at specific characteristic frequencies associated with the rolling elements and raceway. Spalling in gears and sprockets occurs at the most critical contact point, the tooth surface. This often occurs due to cyclic loading and high concentration stress, especially in gears under heavy loads. These cracks on the gear teeth surface leads to spalling, causing pits that generate impact frequencies. Impact frequencies from spalling affect the gear mesh frequency and harmonics as high-frequency peaks in the spectrum. These harmonics arise due to repeated impacts as each gear tooth passes over the spalled area, creating distinct vibration peaks at multiples of the GMF. Spalling in sprockets is less common in sprockets than gears and bearings, but can occur under high loads or in cases of poor alignment or lubrication. Like in gears, spalling in sprockets occurs at the most critical contact point, the tooth surface. Impacts at the engagement frequency of the sprocket teeth with the chain links, creating distinct vibration patterns that can be identified in the frequency spectrum. These harmonics are generated by the repeated impacts as each chain link engages with the spalled sprocket teeth. Spalling in bushings is the rarest, however, under high stress, inadequate lubrication, or contamination, material on the bushing surface may wear down, leading to small pits or flakes. Unlike gears or bushings, bushings don't typically produce sharp, high-frequency peaks, so the spectrum mainly shows lower-frequency components associated with surface wear or rotational impacts. We've covered the basics of spalling, including its definition, calculating the ball pass frequency inner, BPFI, and understanding its effects on bearings, gears, sprockets, and bushings. Now, let's shift our focus to condition monitoring tests that are specifically designed to detect spalling in these components. By using these techniques, we can catch early signs of wear and prevent costly breakdowns. To identify spalling effectively, several condition monitoring techniques can be used, each suited to different types of components and stages of spalling. First, vibration analysis is often the primary method, especially for components like bearings, gears, and sprockets. Spalling creates distinct vibration frequencies and harmonics from repeated impacts. By analyzing these frequencies, vibration analysis can catch spalling in rotating parts. Advanced techniques, like envelope detection, can even pick up early-stage spalling by focusing on high-frequency impacts. Next, ultrasonic testing is ideal for spotting early-stage spalling, particularly in bearings. Ultrasonic waves reflect off irregular surfaces, which helps detect tiny cracks or spalls before they progress. This method requires specialized equipment, but is very effective for surface-level spalling detection. Another valuable tool is acoustic emission testing. It's highly sensitive and can capture high-frequency sounds from crack formation or material flaking, which are clear signs of spalling. This technique is excellent for early detection, particularly when monitoring bearings and gears under load, as it captures energy released during surface degradation events. Finally, oil analysis can be used to supplement other methods in lubricated systems. Spalling can release small wear particles into the lubricant. By analyzing the oil for metallic particles, we can detect spalling before it severely impacts performance. This concludes our video on spalling in bearings, gears, sprockets, and bushings. If you liked this video, please click the like button, share, and subscribe. Until next time.